Okay, well, welcome to our next session of IPAC, which will feature George Seelinger, University of Michigan, speaking on raising operator formula for Macdonald polynomials. So George is part of this very successful research group, which Francois has affectionately labeled BIMPS for Blasiak, Heyman, Morse, Kuhn, and Seelinger. And they have all sorts of great results with kind of a new method, including the proof of the Lower-Warrington conjecture, the rise version of the delta conjecture, and a generalization of the rational shuffle conjecture. And one of their latest things is on this new raising operator formula for the modified Macdonald polynomials. So we'll now turn it over to George.
All right, yeah, thank you, Jim, and thank you to the organizers for having me, and thank you all for being here to listen to me. So yeah, I guess so. Since this is a series of three talks, it'll be nice because we'll have a chance to sort of dive into a little bit more of the technical details and really expand on what some things mean, which is sometimes a little difficult in just like a 1 hour talk. So, but still, just to start, I want to talk a little bit about some motivation. So, if you read through Macdonald's book on symmetric polynomials, you'll notice that he uses these things that called raising operators that aren't always like very prevalent in the literature. But so the idea is that if you have some pair of integers, I less than j, and let's say some integer vector of length L, then he defines R sub ij to act on this integer vector by just taking lambda and then adding 1 to the ith position and subtracting 1 from the jth position. He calls this a raising operator. Okay, so also I want to try and throughout not ever really define things without giving examples. So I'll try and give a lot of examples. So for instance, if I apply R12 and to, let's say, some of our favorite integer vectors as combinatorialists are actually just partitions, right? So maybe if I apply it to partition, say 3, 2, which so I'm going to be using French notation throughout because that's consistent with the paper that we're doing, then, right, I would get the partition 4, 1. And so Macdonald was using English notation, so raising was a nice word for it because the boxes were going up, but for us, they would be going down, but it still raises the partitions in dominance order. So, that we can still think of them as a raising operator in that sense. So he defines these sort of combinatorially, but then he starts applying them to bases of symmetric functions. So like, for instance, if you look at Macdonald's book, even as early as chapter 1, 3.4 double prime, he writes down this formula for a Schur function, which, if you don't know what some of these things are, it's okay. We'll maybe get more precise with things, but I just, want to write down some motivation, right? So he says, okay, I'm going to say a Schur function in terms of something called complete homogeneous symmetric functions is a product over all I less than j of 1 minus rij applied to h lambda, where h lambda is a complete homogeneous symmetric function. And where, okay, what does it mean to apply rij to, say, h lambda? Well, you just apply rij to the indexing partition like that. And so when we say raising operator formula, this is what we mean. Like, so this is a raising operator formula. Okay. And in this case, this raising operator formula is actually equivalent to the Jacobi-Trudi identity, which is another way to write Schur functions in terms of complete homogeneous symmetric polynomials. But it sort of has a slightly different flavor and feel when you're working with it. So for instance, right, if I wanted to do this with S42, right? This would be 1 minus R12 applied to H42. And that tells me that, okay, the H expansion is H42 minus H51. Okay, I already found a mistake in the notes that I posted on Dropbox. Okay, so that's sort of a calculus that Macdonald presents in his book, but there's some confusing subtleties about how to actually work with these raising operator expressions. It even leads to some incorrect proofs in Macdonald's own book. And so sort of the first thing I'd like to do is sort of put this on a more rigorous and sound footing that will also end up sort of exposing me what's going on with these raising operators in a more illuminating way. So to do that, I have to start first by introducing the idea of what I'll call a virtual GLL character series. Okay, so to do that, I'll first sort of define in terms of polynomials an irreducible GLL character. So if I have any integer vector, then I want to define an irreducible GLL character, which I'll denote chi lambda of z. And it's going to be a Laurent polynomial over, I guess we'll just mostly be taking k here to be any z q or whatever. But it's a Laurent polynomial in L variables. And it's given by there are many formulas, but one formula that's sort of suitable for our purposes is we'll take a sum over all permutations in the symmetric group on L letters. And we'll have permutations act on variables by permuting the labels on the z's. And so this will be z1 to the lambda 1 down through zl to the lambda l divided by the product of I less than j of 1 minus zj over zi. Okay. And if you want, you can rewrite the denominator in maybe a form that's more familiar with some people who work with symmetric polynomials, where I instead can write I less than j, put zi minus cj in the denominator. But to do that, I had to multiply by a bunch of by a monomial in the numerator. So I get z1 lambda 1 plus l minus 1 down through zl lambda l. Okay. And this is still sum over all permutations. Okay. And so this maybe to those who are in the know, they this might be recognizable as the Weil character formula, but if not, it's okay. All we really need to know about it is that this is some sort of determinant over a Vandermonde determinant. Or really just a ratio of two determinants. Okay. And so one of the first sort of useful things about this is that, or one of the first sort of interesting things, we should notice, right, is that this is going to be a symmetric Laurent polynomial. So really, I'll write a superscript SL here to indicate that it's symmetric in all the variables. Okay. But these things are not all linearly independent. There are relations between them. And so I want to, in particular, we want to write this in terms of things that are called dominant permutations. Do I want a sign in the numerator? I don't think I need it because I think the signs from the two different determinants end up canceling out. but maybe we can check that afterwards. Okay. So let's see. So if I have any, right, lambda in z to the L, and let's define rho to be a certain integer vector, L minus 1, L minus 2, down to 1, 0, then if I have my irreducible DLL character, I can rewrite it in terms of, or I can write it in terms of weights integer vectors that are sorted into decreasing order. So I can write it like this: a sign of some permutation, which I'll define in a second, but sort of importantly, I can, on the indexing of the GLL character, I can write sort of lambda plus rows, and by sort, I mean putting it into decreasing order, and then subtract off this row. And I can do this if lambda plus row has distinct entries. And otherwise, if lambda plus row has repeated entries, you actually just get 0. Otherwise, okay. And so this is where I have to tell you what W lambda is. So it's some permutation that actually implements this sorting that we want. So such that W lambda plus row is equal to the sort of lambda plus row. Okay. And so this is nice because it'll actually then we now can have sort of relations between these things, and we can distinguish what's called dominant weights or integer vectors that are in decreasing order. So for how do I prove this? Well, I'm not going to actually write out all the proof, but basically these things just follow from manipulating the determinants. So when you get 0, it's because you have two columns that are equal. And so your matrix is not full rank, and you, of course, get 0. And then the other identity just follows from determinant rules for swapping columns. Okay. So let's do some examples, but maybe one other sort of general remark that will help us with our examples, especially if to connect to things we already know. So if lambda is a partition, so an honest partition, there's no negative entries. So in other words, lambda L is greater than or equal to 0, and it's in decreasing order, then right, chi lambda of z ends up just being a Schur polynomial, right? So I hope most people know what a Schur polynomial is, but if you don't, then you can also just take this to be the definition of a Schur polynomial. So it's sort of a win-win either way. So right, a partition, of course, means that we have decreasing entries. Okay, so let's do some examples of this straightening rule. So the first thing is, let's say chi of 2, 0, 1 z. Well, so this ends up just being 0 because if I take 2, 0, 1 and I add row to it, which in this case will be 2, 1, 0, then I get 4, 1, 1. And right, this has repeated entries. Okay. Another type of thing that can happen, let's say like chi of 2, negative 1, 1 z. Well, this will end up being minus of chi 2, 0, 0. And that's because if I take, right, 2 minus 1, 1, and I add row to it, right, then I'm going to get 4, 0, 1. And now that's not sorted in decreasing order, but I can sort it with a simple transposition. So I get 410, but that's going to have a sign of -1, right? So that's where the -1 is coming from. But then to get the indexing, right, I need to then take indexing partition in this case. I need to take 410 and subtract out row. So I get 200. Okay. So, okay, is that rule kind of clear? I hope, and from these examples, and then just like an application of the formula in the case where like we don't have positive entries indexing our partition or our indexing weight or integer vector. We write let's just do the say like 1 comma -1 in two variables, let's say z1 z2, right? If I want to actually just implement that formula above, I'm going to get something like z1 squared z2 to the -1 minus z1 to the -1 z2 squared all over z1 minus z2. And if I rewrite this in as z1 inverse z2 inverse of z1 cubed minus z2 cubed over z1 minus z2, then right, we can those two polynomials, one is divisible by the other, and so we get z1 inverse z2 inverse of z1 squared plus z1 z2 plus z2 squared. Okay. And so you people who have spent a lot of time working with Schur polynomials like I have might recognize this as s s20 of z1 z2, or right in our notation that's the same thing as chi20 of z1 z2. And so this suggests a general fact that I'll tell you, but not sort of bother proving, which is that if I take z1 through zl and I multiply one of these characters by that in L variables, then all I'm going to do is end up adding 1 to every weight. So this is length L. Okay. And so sort of the upshot of that is that if you're sort of more familiar with the world of Schur polynomials, in some sense, that's all there is to this. You can always, if you have things that are sort of too negative and you're in the Laurent polynomial world, you can kind of just boost it up by factors of z1 through zl multiple times until you're in the polynomial world, do whatever sort of manipulations you want, and then just undo that at the end. Okay. So yeah, that sort of is what I wanted to say about these characters. But then I want to, so these will end up being sort of the building blocks of all of these raising operator formulas that we'll end up using. So then I want to package sort of those ideas into a map. So let's take now just any Laurent polynomial. Okay. And I want to define what I'll call Weyl symmetrization of this polynomial, which is going to be this map so that it's a bold sigma in the paper, but when I want to bold something, I'm just underlining it on my paper. So this is the same sort of sum over SL, but now, right, we'll put just this Laurent polynomial in the numerator, and then we'll put the denominator that we saw before from the GLL character formula and the denominator. Okay. And so the reason for this, right, is like really, so what you're thinking is that it's sending each monomial So if I write sort of z lambda, I mean like z1 lambda 1 times z2 lambda 2 up to zl lambda l, right? But this is sending each monomial to the corresponding GLL character. Okay, and we call this Weyl symmetrization. So it's a way to take a Laurent polynomial and symmetrize it. Okay. So the other thing that we will want to do though is these Laurent polynomial terms in general will end up getting a lot of the identities that we want to show are in the world of symmetric functions or symmetric polynomials. And so we don't want to be dealing with symmetric Laurent polynomials. We really want symmetric polynomials. So what we'll define then is, so if we take, let's say capital lambda is our symmetric function ring. So this is symmetric functions in formal alphabet. Let's say call it X. So if this word sort of is meaningless to you, you can just think symmetric polynomials in an infinite number of variables. But what we want to do is then we'll set this map pol sub X. So it's pol is short for polynomial. That will apply, the domain will be symmetric Laurent polynomials in, say, L variables, and we'll map them to our symmetric function ring via sending linear, we'll take the linear extension of just sending each character, each irreducible GLL character to either the Schur function, if that makes sense, right? So if let's say that this is only for, we'll do for the ones where we have dominance, or where they're weakly decreasing, let's just say. So then if UL is greater than or equal to 0, after we've written it in this, each of the characters in this form, we can send it to a Schur polynomial, and it's indexed now by an honest partition, so that makes sense. And so if we have a negative entry in the tail of our integer vector, then we'll just send it to 0. Okay, so that part doesn't contribute. Okay. So now we have all the tools to sort of, in a precise sense, say that some of these identities that I mentioned at the beginning in Macdonald, for Macdonald. So theorem. So let's take, say, any lambda in any integer vector, then the complete homogeneous symmetric function h lambda is just given by the polynomial part of the Weyl symmetrization of z1 lambda 1 down through cl lambda l of the product over I less than j of 1 minus the igzj, where, so there's some interpretation that's going on here, so where these denominator factors, we're really thinking about them as geometric series. So this is 1 plus zi over zj plus zi squared over zj squared, and so on. Okay. Right. And so in the world of sort of like Macdonald land, he would have written these zi over zj's as rij's, and would have been writing them as acting on the basis of, say, Schur polynomials. But in a sense, that's sort of confusing, and I feel like this sort of makes everything more precise. Now, you might look at this and you might say, okay, George, but there's something wrong here, because if I look at what you just wrote down, this is an infinite series of terms. But importantly, maybe if we do an example, we'll see why we don't need to worry about that. So if I take, let's say, H42, right? So this is polynomial part of the Weyl symmetrization of, say, Z1 to the fourth, Z2 squared. And then I'm just going to expand out this denominator term, Z1 over Z2, Z1 squared over Z2 squared. Let's go out to the cube even, Z1 cubed over Z2 cubed, and so on. Okay. And right, so when it is true that when I symmetrize this, each of these things, right, I'm going to get a bunch of GLL characters. So chi 4.2 plus chi 5.1 plus chi 6.0, chi of, 7 minus 1. That still looks like a z, sorry. Okay. And so on. Okay. But right now, looking at this, what this polynomial part function does, right, is it's going to kill off everything where if it's in decreasing order, we don't need to do any of that sort of straightening rule that I showed you. We just can check immediately, right, everything. And here is just going to get mapped to 0 by the polynomial function, the polynomial part function. And so all we're left with then is S42 plus S51 plus S6. Okay. So maybe I'm going to pause here for a second because I feel like I sort of blazed through that a little quickly, but also because this is sort of like crucial to understanding, right, how these formulas work.
Well, I did have one question, George.
Yeah.
So you have ZI over ZJ where I is less than J here, but above was it
Mhm.
ZJ over ZI?
Yeah, right. So, but there, so yeah, this you're very astute here. So there, the right, this factor right here is not a geometric series. So, right, because of how right, because of the construction, we're going to end up getting this will be honest divisibility. So this um this part will just divide out and you'll get, right, like, you can think about this map as just sending each monomial to an irreducible GLL character. But then now inside of this sigma map, when I'm down here, yeah, it's Zi over Zj, because that's like the raising operator Rij, that's actually raising the weights of these things. So yeah, these things are to have a resemblance to each other, but we're sort of treating them in very different ways.
I see. Okay.
Yeah. Yeah. In some sense, this factor you up here, I wish, or where's the laser pointer? Oh, that would be better. Okay. This factor up here, like, we probably won't ever really need to think about it again because we've packaged it into this sigma map. And for sort of practical purposes, yeah, you're just thinking about sigma sending each Laurent monomial to a character. Um, and then but then every other sort of denominator factor that I'll be using in the I sort of Zi over Zj form will be thinking of as geometric series and not on it. There won't be divisibility happening there. Yeah, no, it's a confusing point. um, okay.
What
Oh
it's
yeah.
quite silly, but what happens if you take var symmetrizer twice? Is it
um yeah, then nothing will happen.
okay? Okay.
Yeah, yeah, because yeah, if you Weyl symmetrize something that's symmetric, you can just pull it outside the symmetrizer. Yeah. No, that's not a silly question. It's a very good question. Okay. Maybe just I'll make some other remarks about this construction. Well, maybe I already, yeah, I mean, I already said them in words, but right? So one is that only a finite number of terms survive the polynomial part operation because of the fact that we're sort of eventually, right, if you apply enough of these zi over zj's things, you're going to get really negative, and even after the straightening rule, you'll end up with a negative tail and just get sent to 0. And the second point was that, like, the traditional notation for this in Macdonald's book, right, looks more like this. So 1 over product of I less than j of 1 minus rij applied to s lambda. Okay. But I sort of don't want to get into what that means because, yeah, there's sort of more subtleties in the way that Macdonald defined how these rij's acted, and I think sort of the treatment I gave is in a sense sort of the rigorous way that we think about it these days. Okay. So then, sort of as another sort of setting the stage, I'd like to sort of, and getting some practice with these things, I'd like to actually then, and I know this talk is about Macdonald polynomials, but probably in this first talk, we won't ever actually get to Macdonald polynomials, but a precursor to Macdonald polynomials was Hall-Littlewood polynomials. And the sort of approach to Hall-Littlewood polynomials had been done in various ways and forms prior to any of our work. And so I think it's sort of helpful to look at one particular example, the work of Marksham, Mizono, and Wayman, to get some practice with these sort of the style of raising operator formulas, and to understand sort of maybe set the stage for where we were coming from when we started looking at the Macdonald polynomials. So to do that, I first need to define sort of a new combinatorial object, and that is the set of positive roots of GLL. So I'm going to write R sub plus, or make R sub plus of GLL, and this is going to be a collection of vectors alpha ij for I less than j, where by alpha ij, I mean I want to take the ith coordinate vector and subtract off the jth coordinate vector. And these are this is called, it goes by many names, but I'll call them the positive roots for GLL. And then associated with these roots, this collection of positive roots, we can define something called a root ideal. So a root ideal, maybe I'll call it capital psi, is some subset of these positive roots, satisfying that if alpha ij is in my root ideal, then I also need to have all of the roots whose first component is less than or equal to I. So for all I prime less than or equal to I, and also whose second component is greater than or equal to the second component. So I mean, this is something that I think is much better seen in a picture or an example. So let's do, say, L is 5. And so to these things, you can actually draw them out quite nicely. So I want to imagine whenever I'm talking about these root ideals, I'm going to draw them in matrix coordinates. So I imagine that they're in sort of in this case, like a 5 by 5 box here. Oops. And right, because I'm only taking I less than j, right, I can only get these things that are strictly above the matrix diagonal, and so on. Okay, and I can imagine each box corresponding to one of these positive roots. And then a root ideal is going to look a certain way. So it's going to, if I have a root, like let's say I have this root right here, 1, 3, then I need to have all of the roots above it and to its right in this picture. So to be a root ideal, I also have to have this root and this root. And then let's say I also, for instance, I decided I was going to have this root 3, 4 in there. Then once again, I need all of the roots to the right and above it. And then of course I need all the roots to the above and to the right of the one I just drew, right? So I get something like this. And if you sort of do like enumerative type combinatorics, you might recognize that this looks familiar. It actually looks kind of like a dict path. And that would be sort of another way to describe it. So actually a root ideal in type A is if you just draw a dict path, it's a root ideal if you have all of the roots above a dict path, and none of the roots below it. So this is a root ideal. Okay. And yeah, so in general, so root ideals in our case for GLL are in one-to-one correspondence with dict paths. Okay. So let's see. Right. So then I want to just describe, following Shimizuno and Wayman's paper, a certain class of root ideals. So I want to take mu to be a partition of L. And then I want to write the set, say 1 through L, into a bunch of disjoint unions of intervals. So I sort of struggled with the best way to write this out. Right, this is, so I want to write it as a bunch of disjoint unions of intervals, each with, where the length of, or the number of elements in AI is mu sub I, right? So this is going to look something like 1 up to, right, mu sub L mu. It's a little recursive, but that's okay. And then I want them to just be like, this is the simplest set way to break up this set. So then the next interval starts at mu L plus 1 and so on. Right, so you could formally say something like, and right, the max of AJ is equal to the min of AJ minus 1 minus 1. And these are all intervals. So I'm not like skipping anything. Okay. Right, so maybe just an example. I feel like examples always illustrate things a little better. Like this, like if mu is say 3, 2, which is a partition of 5, then right, my set 1 up to 5 is going to be the interval 1, 2, and the interval 3, 5. And I mean the combinatorial intervals here. So I'm just taking integers. Okay, so then with this construction, I can define something called a parabolic root ideal. So then we have a parabolic root ideal. Mu, and that is going to be the collection of roots alpha ij, where I and j are in distinct intervals. Maybe once again, sort of a picture helps illustrate that. So let's keep like 3, 2 is our example because we already wrote out our intervals there, right? So, and if I draw out my picture, right, I have sort of 1, 2 is one of my intervals. So like I'm not gonna be able to have 1 comma, the alpha 1, 2, because then I and j would both be in the same interval. And similarly, I can't have anything in this box. So I can't have alpha 3, 4, 3, 5, or 4, 5. But then I have all of these other roots outside of there, because this has that, the I is in the first interval and the j is in the second interval. Okay. And so sometimes this is a little faster to even just draw out this picture, because all you need to do is draw, going from bottom to top, these boxes based on the size of the parts of your partition, and then exclude those roots and include everything else. Okay. So why did I define this parabolic root ideal? Well, because Shimizuno and Wayman give a way to, or a formula for Hall-Littlewood polynomials using parabolic root ideals. So following result is due to Shimizuno and Wayman. And so if I have any partition of L, then the, let's say, modified Hall-Littlewood polynomial, I'm gonna sort of use some ad hoc notation here, and I'll explain why in a minute. So this is going to be a symmetric function, but it's going to have now coefficients, and say a priori they're going to have this extra parameter t in the coefficient ring. So now I have symmetric polynomials, or symmetric functions, but I can have these rational functions in t in my coefficient. So this is given by h mu of xt is going to be omega, which I'll explain in a second, of the polynomial part applied to the Weyl symmetrization of, in the numerator, we'll just have z1 through zl, and in the denominator, we'll take the product over all of the roots that are in the parabolic root ideal, this b mu associated to the indexing partition, 1 minus t zi bj. Okay. Where, as before in my other example, this is geometric. These are all geometric series. Okay. And where omega applied to a Schur function will send the Schur function to the one indexed by its transpose partition. So you just, in French notation, if you have some shape, you reflect it over the x equals y line, and you get the transpose partition. This is transpose. Okay. And so, if the theory, if you don't know what a Hall-Littlewood polynomial is, that's fine. I think this is actually you could just take this as your definition of a Hall-Littlewood polynomial, and I think it's a good, or maybe even a great one to take. But also for the experts in the room who might protest, I'll just mention that there is a slight change of conventions here. So the usual Hall-Littlewood polynomials, which are typically denoted without a tilde on them, are differ from these ones by a t to t inverse swap. So if I just change t to t inverse, and then I bump up the weight, the t's appropriately, so that they're all polynomials and there are no inverses in the expression. you get that. But that's just a remark for the experts. For our purposes, it will be sticking with this formulation of Hall-Littlewood polynomials. So let's do some examples, and then we probably won't have time for too much more than that. So let's just take, say, these examples, if small examples, even enough to illustrate what's going on. So let's take mu to be 2, 1. So our parabolic root ideal is, right, if I do sort of my box drawing trick I showed you before, I draw a 2 by 2 box and a 1 by 1 box and exclude everything in those roots, and I just get these two roots. Okay. And so then writing it all out, h21 tilde x t is omega of polynomial part of x of the symmetrization of, so we'll have these two root denominator factors that we're expanding out as geometric series. So we have 1 plus t z1 over z2 plus t squared z1 squared over z2 squared, and so on. And then we also have another one for the root 1, 3. So z1 over z3 plus t squared z1 squared over z3, and so on. And then all of this is applied, or we also have a factor of z1, z2, z3, okay, all in that Weil symmetrization. Okay. And so if I just multiply out all those monomials and then turn each of them into a character, a GLL character, I'll have omega, the polynomial of x, of chi 1, 1, 1, plus, and so I find it sometimes easiest to just do this one t factor at a time. So the roots that, or the factors that contribute a single t, well, I have z1 over z2 and z1 over z3. So those will turn into I201 plus, or in chi of 210. Okay. And then for the t squared factor, I'll get I of 3, 1 minus 1 plus chi of 300 plus chi 3 minus 1, 1, and so on. This is an infinite series, but just like before, I know that eventually when I go far enough out, this polynomial operator is just going to kill them all anyway, and so I don't need to compute too far out. Okay. Right, and of course these came from either applying, like you have z1 squared, z2 squared, z1 squared, z3 squared. I forgot that right there. And then of course you can have one z1 multiplied together with one, or one z1 over z2 with a z1 over z3, and that's why I have three terms here, and so on. Okay, and so now let's apply this polynomial part operation to just the ones that we have here. So this will become the shear function S111, and then 201, we actually did that example before. That's just 0. And then this is S21 with a T on it. And then, so 3, 1, minus 1, that's already in decreasing order, but it has that minus 1 in its last entry. So that's just 0. This is T squared, S3. And then 3 minus 1, 1. We haven't done that literal example, but it's one of these other rules that will get changed with a minus sign, and it becomes also an S3, but with a minus sign. And then you can maybe just take my word for it that the rest of everything else beyond is 0. Okay, and so and there's still an omega here. I haven't finished with that. But now, right, you can see that these two S3s are just going to cancel out inside this expression. And all that we have left is an omega applied to S111 plus T S21, which is just then S3 plus T S to 1. Okay. I think also when you have sort of formulas like this, it's worth looking at the extreme cases just to sort of check our intuition and sort of see what's going on. So right, if mu is equal to L, then right, B mu is going to be the empty set, because there's no way to take 1 through L, partition it into one block, and then take indices from two different blocks. And in that case, HL T is right just omega of the polynomial part of sigma of just Z1 through ZL. We have no denominator factors there, right? And so this is just going to become omega of S1, or, with L1s here. So that's just SL, or it's also called HL. And then finally, on the other extreme, right, if we have mu is equal to all ones, 1, 1, 1, 1, 1, 1, then right, B mu will be everything, all of the positive roots. And right, so then H1 to the L of X E is omega polynomial part of X sigma Z1 through ZL over the product of, now we have all of the roots. So that's the same thing as just saying that we have all I less than J, the 1 minus T ZI over ZJ, like this. And if we take this formula, right, and we put T going to 1, then we recover, right, so if we take T to 1, then that formula becomes the formula we had before for little h, the complete homogeneous symmetric function. So we get omega h little h 1 to the L, which is just the same thing as S1 to the L. So in this case, we have some sort of like T deformation of the product of L sure functions S1 to the L. Okay. And so then I just want to end right with one sort of corollary, which is sort of an important part of what all of these raising operator formulas give us, which is that you can kind of see, at least in the low degrees of T, what's going on, right? You can see that all of these, oh, oops, and I should have had a tilde on all these H's here. So all this is always going to have, right, after we apply omega, it's going to have in the lowest T degree just an SL of X, and then plus T and a bunch of other stuff. Okay. Yeah, so I think for what I wanted to say, this is in the time, this is a natural stopping point. So I feel like it was a little technical, and so I welcome questions about these things, but this will sort of set us up for the next few lectures to really understand what's going on in the paper.
All right, let's thank our speaker. Very good. And any question? I guess there was one in the chat.
Yeah.
Somebody wanted to make sure that this was really modified Paul-Lewis.
Yeah. So here, I mean, yeah, like all of the computations I was doing, I should have put tildes over everything. So I'll never be using the standard H's. I'm always using these like ones that have been swap, T inverse swap. And also, just as a warning to those who are not familiar with this is very not standard notation, so don't. But there was sort of no good way. I don't know of a great notation for these things.
So in this example you gave, you have this nice Schur expansion. Now, is there a known way to get the Lascaux-Schutz and Berger formula by canceling terms?
I don't think that not that I'm aware of. Maybe there is, but the yeah, I don't know how to do that.
Uh, I don't know either.
I
So
like there are,
assume
I
that.
know other ways to get the formula, but
Yeah. I was just
not with
kind of
this
thinking ahead
specific.
to if you had some Macdonald version of this, apparently you do, then you
Mm.
could get some QT expansion in terms of Schur's.
Right, right.
Yeah.
Yeah.
Okay.
I think so Anna has some work with Jonah Blasiak and Jennifer Morse on ways to recover in certain cases sure expansions of these sorts of raising operator formulas. But it doesn't apply like to all, there's certain conditions on what the root ideals have to look like in order for that to go
Ah,
through. And I don't know if this falls under that case or not. I think it doesn't, but yeah, Anna's shaking her head.
Right, right. So kind of a broad question, kind
Hmm.
of in this Hall-Littlewood formula and later with your sort of cattle animal objects, you have
Hmm.
parameters like Q, T, QT appearing in the denominator and hence in geometric series. Francois Bergeron
Hmm.
has, this whole program of trying to work with like even more than two sets of variables.
Hmm.
Do you have anything for like, more parameter variables that can appear in the denominator, more root ideals you can consider?
Yeah, I mean, so I think like the answer is there should be something like this, but the computational complexity of this becomes pretty difficult to investigate. And I don't, at least like in the things you can kind of come up with some guesses as to what, if you are familiar, and maybe I'll get more into cattle animal stuff, or I should get into that more in the next talks. And you can come up with some guesses, but sort of the most obvious guesses end up breaking down once you get into high enough degree. And pushing these things into high degrees is difficult because you're expanding these geometric series. Right. And so as you add more denominator factors, your computational time is going way up. So, I think that's something that I'd be very curious to figure out more about. And I have talked with Francois a little bit about these things, but sort of there's no sort of clean and elegant answer that I know of at this time for how to sort of go forward with that.
Any other questions? Okay. Well, I guess we'll look forward to Thursday then,
Yeah.
and
Okay.
we'll
Yeah. On
see you all
Thursday, I
then.
plan to. Yeah. Yeah. Sounds good.
All right. Great.
All right. Thank you,
Let's
everyone.
thank our speaker again.
Oh, yeah.
All right. We'll see you guys on Thursday. Bye.
See
Bye.
everyone on Thursday.